Hi and welcome. We'll give it another minute here before we get started. All right, well, let's get started. Welcome to this Tecton webinar. My name is Sergio Farragut. I'm a developer advocate here at Tecton. And today we're hosting Niccolò Ronchetti from Block with his webinar about building a resilient real-time fraud detection system at Block. So Niccolò is after graduating from Stanford University with a PhD in mathematics in 2017. Niccolò spent 3 years at UCLA as an adjunct assistant professor. And in 2020, he made the move to the industry after a short stint in the finance sector. Niccolò joined Square in the summer of 2021 as a machine learning engineer and has been part of the fraud detection team since then. Welcome, Niccolò. The floor is yours.
Thank you, Sergio. So thanks everybody for coming. Thank you to the Tecton team for inviting me. What I'm going to talk about today is how we built a resilient and real-time fraud system at Block. This is a project that took quite some time and required the collaboration of many teams, not just my team, the fraud detection team at Block, but also the Block machine learning infrastructure team, and of course, Tecton support. So I want to thank everybody involved with this project to begin with. So within Block, I am part of the fraud detection team at Square. Square is one business unit within the Block ecosystem. And we're going to get more into the Block ecosystem in an upcoming slide. In this talk, I'm going to discuss how the fraud team is coming up with innovative solutions that allow us to scale up with the speed required to make the Block ecosystem grow and launch new products, new features as often and as soon as we want. So this is the agenda for the talk. First of all, we're going to talk about why we have a scaling and speed problem. Then we're going to talk a little bit about what does it mean to use bias for fraud detection. We're going to talk about how this theoretical framework was implemented using Tecton. And then we're going to spend quite some time talking about the challenges that we had when we were trying to implement this through Tecton and the learnings from this project. So let's start by talking about the Block ecosystem. This one here is a one-year-old perspective on the Block ecosystem. So in the past year, we added quite a few more features, quite a few more products. But let me start by describing the Block ecosystem. So the Block ecosystem has Square, which is the business unit I belong to. And Square is serving businesses of all sizes. Square customers, which we call sellers, are small and large businesses that hire Square for all their financial needs. The other major, bigger business unit within Block is Cash App. So Cash App is a business unit serving individuals. You are probably all very familiar with Cash App as a peer-to-peer app, which also offers now financial products like debit cards for everyone who is eligible. We also have some smaller business units, Afterpay. Afterpay is a business unit for buy now, pay later customers. So if you want to buy something which is quite costly and you prefer to have a delayed payment at regular intervals, this is where Afterpay comes in. We have Tidal, business unit serving artists, mostly musicians and singers, I think, but in general, artists. Hardware, Spiral, they all fall into this general sector. So I want you all to notice a few things about this ecosystem. First of all, new entry and exit points are constantly launched and added to this picture, especially in Square and Cash App. So what do I mean by entry and exit points? I mean new products and new features which connect a Square account or a Cash App account with the outside financial ecosystems. And not only each business unit is strongly self-connected, and you can see that by all the arrows, for example, within the Cash App circle that are internal to this circle, pointing from one Cash App product to the next. So not only each business unit is strongly self-connected, so that users can leverage many different products within the same business unit, but there are also quite a few connections between different business units, especially connections between Square and Cash App. And this is by design, right? We want our customers to be able to leverage the Block ecosystem to its fullest. And so if you want to move your money from Cash App to Square, you're free to do that, and also in the other direction. So this is quite a complicated ecosystem. So let's talk about.
Let me interrupt for just a second before we jump into fraud detection. Can you tell us a little bit about the overall machine learning and AI landscape at Block?
Sure. So like many other companies, Block uses machine learning for many different needs. Now, Block is a fintech company, so risk and fraud and credit risk is probably the most pressing need for machine learning. And I think it might probably have been the first machine learning team that was established back then. But we also use machine learning for a variety of other goals. We have machine learning teams dedicated to growing our platform, to serving our users, to recommending them the best products. We have machine learning teams aimed at helping people, helping businesses build their website. So we try to use machine learning in every possible way where it's well suited to help our customers. And the risk team is one of the bigger teams.
Very interesting. Thank you.
Mm-hmm. So this is a very complicated ecosystem, as I was saying. The fraud team is responsible for detecting, preventing, and stopping any kind of fraud and abuse on the Square ecosystem. And for the remainder of this talk, I'm mostly going to focus on Square, since this is a business unit I've always belonged with and where I have the most experience. So fraud and abuse, unfortunately, have many facets, and they could target Square, meaning that people could try to steal money from Square, from us, from the company. They could be targeting our users, our sellers, so trying to steal money from our customers, or they could be targeting both. And these fraud and abuse could have either financial or reputational implications, or both. Now, if we think back about the growth of the ecosystem and the number of new products and features that Square is launching, and this keeps increasing and is always faster. And many different product teams have go-to-market launches this quarter, either by launching new products or by launching new features within existing products. And every time that we have these new products and new features, they make the ecosystem more complex, and they often introduce new avenues that connect a Square account with the outside world. So what do I mean by this new avenue is essentially new ways in which money could be entering the Square ecosystem, or it could be exiting the Square ecosystem. And every one of these avenues poses risk from a fraud perspective, right? Bad actors could use this new avenue to exit from Square money that they stole, and that money is lost and someone like Square is liable for it. Or they could use an avenue to instead bring into Square fraudulent funds. And obviously, we don't want either of that to happen. So the fraud team needs to keep all these avenues safe. And here is our scaling and speed challenge. How do we keep scaling up our fraud controls so that all these new avenues are covered without blocking and slowing down the go-to-market schedule of the product teams? So this is where this Bayesian approach comes into play. And Thomas Bayes, which was a mathematician, a probabilist, a jack of all trades, like many scientists in the past, set up the following probabilistic framework. when you are considering the probability of a certain event, so for example, the probability that a user is a bad actor, you should constantly adjust your priors every time you encounter new evidence. And I think here, the keyword, at least for this talk, the keyword really is adjust. We don't mean that every time we discover new evidence, we should, recalculate everything from scratch and reconsider our position as if we didn't know anything. We should, adjust, make a little update on our probability that the user is a bad actor. We don't need to recalculate everything from scratch. We just need to update our perspective, update our prior. So this is all, so nice and good from a theory perspective, but how do we actually use this? So to use this, we need to basically identify what we could use as prior and what we could use as new evidence. For priors, we could take on any given user our fraud model score for models evaluated on either of the following type of events. We could either consider the fraud model score on bottleneck events, and then I'm gonna call an event to be a bottleneck event if it's an event that every user needs to go through. So typically this is account sign up, right? Every user that wants to sign up for Square, well, you need to sign up, you need to create your account, and we do run a fraud evaluation when you create your account based on a number of indicators. And so this is a bottleneck event because every user needs to go through it. Or we could look at high volume events. So these are events for which we assume that most users have a very recent evaluation because most users do these events very often. And the typical example for such an event, at least within Square, is payments, right? If you are US based, you know that Square started off as a payment processing company, so payments are still our bread and butter. And our most long-running product and still our bread and butter is offering businesses a chance of letting their customers swipe a credit card on a Square iPad or on a Square device. So this is taking a payment, and that's still what the majority of our customers, the majority of our sellers do. So this is a high volume event. Businesses, of course, take payments multiple times a day. So this is the type of event that we can take to establish a prior on any given user. And then when any new product or any new product feature is launched, we can update our prior, which is going to be given by the model score on one of these two type of events, with specific event level information. And we will get an updated perspective on the riskiness of the user. And if we go back to the theoretical probabilistic perspective, you can think of this update as our posterior. And one thing I want to mention, fraud is a classification problem from a machine learning perspective. So all the models we're going to talk about today are classification models. And of course, these are very unbalanced models, meaning that fortunately fraud is quite rare. And typically the fraud class is the class labeled as 1. So in particular, higher fraud scores correspond to riskier and riskier events. And this is important for the next slide I'm gonna go through. So let's discuss about an example. Let's suppose that we have a user that signs up to Square. As we said, signing up is a bottleneck event. So every user that signs up to Square will be evaluated by our sign up fraud model, and we will have one fraud score. Can't escape from that. Let's say that this user scores as 0.5 on this fraud model at sign up. And we can think about 0.5 as medium risk. It's not quite high enough to take immediate action, but it's also far from all clear. It's sort of like, let's keep an eye on this. This is our prior. Let's say that the first action that this user takes on their platform once they have signed up to their account is a cash deposit. So cash deposit, even if it says cash, this is actually a Square product. Cash deposit is a new product that launched in spring 2024, and that allows all eligible Square businesses to deposit cash, so literal dollar bills, at a large number of partner locations across the US. So, you run your Square account, you select cash deposit, you figure out where there is a location close to you, a physical location, you go there with your, your bills, your cash at hand, and there's an interaction with the cashier at this location. You deposit your cash, and it gets, and then you see the amount on your Square account. So this is what the product looks like. Now, we can imagine that it's quite unusual for users that sign up to Square to start off their Square journey by depositing cash. After all, Square is for businesses, and businesses make most money by taking payments, and most payments nowadays are really card payments. Let's also say, again, in this hypothetical situation, that the dollar amount that the user deposits is higher than the average that we would expect. And finally, one more information that we collect from this event itself, from the cash deposit event itself, is that the physical location where the cash is being deposited is far from the location of the business that was indicated during sign up. So this is essentially the new evidence. The new evidence is, well, this is a bit higher of a cash deposit. You're trying to deposit it far from where you told us that your business was. And also, this is really the first thing you do. So all this indication, the new evidence, make us update our prior and move this user from the medium risk cohort to the high risk cohort. And once the user moves into the high risk cohort, this high risk cohort results in us taking actions to ensure really that everything is on the up and up with this seller, with this user. And it doesn't matter for the purpose of this talk what actions we take. The point is that it was a combination of the prior and the new evidence that resulted us into moving the user to the higher risk cohort. The new evidence by itself would not have been enough to take action, and neither would be the prior by itself. The prior was only medium risk. It is really the combination of these two. It is really adjusting our prior in light of this new evidence that resulted in us moving this seller to the higher risk cohort.
So
another thing
I'm sorry, I didn't mean to interrupt mid-sentence, but there's a popular question coming on the Q&A that says, how do you calculate a risk score on a new user while they are signing up? Is it using ML or a rule-based approach?
That's an excellent question. We, of course, use complicated ML and a combination of machine learning models and heuristic rules to calculate that score. I can't get too much into the details, of course, but we do use machine learning models.
And one more question that came in: how many features are you using in this model, and any particular reason not to choose other model algorithms?
That's another great question. We use all the features that are available, and then we experiment with different algorithms. And in general, and this is not really just about sign up, in general, our choice of algorithm is a trade-off between, of course, the performance of the resulting model and the speed at which we need to return an evaluation. So this is quite common in the fintech industry. And I think it's common, for example, also in the ads and marketing industry. Like, you need to return an evaluation in a fraction of a second. So you cannot wait too long. And that, of course, impacts your choice of algorithm. Now, for example, the initial LLMs that have been launched, if you remember, they would take several seconds to write a full sentence. And several seconds is just way too long for us. So that's how we choose an algorithm, a trade-off between performance and speed.
I assume it varies, but there's one more question. Do you use gradient boosted trees based models or neural nets?
We use every possible algorithm that provides us a good performance, again, compatible with the speed, and that includes the two algorithms that are mentioned.
Okay. I'll let you move on.
Thanks. So one last thing I want to remark about this slide is that the type of logic that we're doing here, when we have a prior, which was a model score, and then we have some new evidence, this type of logic does not require us to train a new model specifically evaluating the cash deposit attempt. And this is crucial because if we had to train a new model specifically for every new cash deposit event, we would require a lot of available data, a lot of machine learning work, and the day that this new feature launches, we don't have any data because nobody has used it yet. So we would have to wait for data to pile up, and that could take weeks or even months, and we would be unprotected from fraud if we had to wait. So that's how this approach allows us to essentially put in effective fraud controls from day one every time a new feature is launched. And this is a common sense logic that, again, it can be implemented on day one, and then we can monitor and update as more data comes in.
So there's a few questions about the scale. What is the number of signups and number of transactions that you are dealing with in this environment?
Oh, that's a good question. I'm not sure what's publicly available. I think it's safe to say that Square processes millions of payments every day. In terms of the signups, of course, it's gonna be a smaller number because we don't have like millions of new businesses in the US every day. But for payments, really, we're talking millions and millions every day. So it's a pretty large scale considering that we need to evaluate all these payments, again, in a fraction of a second.
That was my next question, latency. So yeah, it's a fraction of a second, right? You have to
Yes.
be able to calculate this within the transaction.
Yeah, exactly. Think about it. When you swipe your card, you are not there waiting for seconds and seconds and minutes. You really needs to get done extremely quickly. And all these network, all these systems have been optimized to an extreme to make sure that we can return a good answer within that fraction of a second.
And a final question, and then I'll let you advance, is you mentioned the data set was imbalanced. The fraud label is imbalanced. Do you generate synthetic data to create a balanced data set?
This is another great question. This is an approach we experiment with. I'm not sure I can say more than that. Sorry.
We'll leave it at that. All right, I'll let you go. Keep going.
So now we talked about the theoretical approach and the implementation that we want to do. We talked about the theoretical approach. Now we need to talk about how we actually implement this. So the main thing we want to do is we need to create features from the data feeds of our own risk evaluations. As we said before, every time that user goes through the sign up, we need to basically create a feature that says the last score of the sign up model for user XYZ was 0.5. And then this feature should become available for any other risk evaluation that user XYZ is triggering in a kind of a feedback loop. And the challenges with this project, which we talked about, especially we touched upon, especially in the questions, are, first of all, our risk evaluations are a very high volume data feed. And as I was saying earlier, millions of payments per day. And not just that, but this volume changes drastically during the day. So it's not overall constant. You can imagine, of course, that most events happen on normal business hours. And then, during the night, there's much less volume. So we need a solution that essentially auto-scales across the day. The whole feedback loop process, sign-up model is evaluated on user XYZ. The sign-up model score on user XYZ is written on this risk evaluation data feed. The risk evaluation data feed is ingested by the feature store, and the feature store updates the feature values from this new event. This entire process should be as low latency as possible. And finally, the resulting feature, again, last score of sign-up model for user XYZ, this resulting feature should be available on the entire Square ecosystem, not just the same type of risk evaluations that is powering the feature, but really the entire Square ecosystem. And we saw that when we discussed the example with cash deposit. We were using a sign-up score on a cash deposit, and those are two very different type of events. So these are the challenges that we have with the implementation, in a sense, the requirements.
So before you dig deeper into the implementation of fraud detection, can you tell us a little bit about what your overall machine learning stack was before Tecton, and how Tecton improved and helped you address these challenges?
Yes, actually, I think I have a slide coming up where one of the first things that we had to think about in this implementation is basically whether we wanted to use Tecton or our own internal systems. So I think I can answer your question at that point. So I'm gonna give you just a very basic design of the implementation at a high level. So we have our risk decision engine that receives risk evaluation request. For example, the risk evaluation request is user XYZ signing up. Risk decision engine give me a fraud score on this user XYZ. This risk decision engine runs all sorts of heuristic rules and machine learning models. And the list of rules and models to be run is, of course, different from endpoint to endpoint. And by this, I mean that evaluating a payment from a risk perspective is a different set of rules and models than evaluating a login. At the very least, you can imagine that when we evaluate a payment, there's a payment amount, and the login doesn't really have any amount associated to it. So of course, different rules and models. Once the risk decision engine completes all the evaluations on any specific event, so user XYZ signs up, bunch of rules and models, the risk decision engine completes the evaluation of these rules and models, and it publishes the result in a Kafka feed, which in this design we're calling risk evaluation. And at this level, at a high level, this feed schema contains one or more identifiers, for example, the user ID, of course, and the scores for all the rules and models that were evaluated. And this Kafka feed syncs to a Delta Live table, which is going to be a data sync. And this Delta Live table is hosted in Databricks. And now this is where Tecton comes into the picture. On the Tecton side, we create a Kafka stream source that is powered by this Kafka feed. And then the Delta Live table where the Kafka feed is syncing into is used as a batch source from Tecton. The Kafka stream source and the batch source together are used to power a stream feature view that is outputting aggregations on this model score, where and they're grouped by the user ID. So in Tecton parlance, the user ID is a entity or the join key. And this is how we got features like last sign up model score for user XYZ. So this is a high level implementation, which is sort of a preview, because in this next slide, I'm gonna talk about the implementation choices that we had to face and why we chose one over the other. And the first implementation choice really, and this goes to Sergio's question from a few minutes ago, was, well, which feature store do you want to use? And the choices, of course, are the Tecton, which is the one we went through, or our internal feature store. So I'm gonna use interchangeably the word feature store and feature system. By feature system, I really mean the system or the systems that ingest and persist the raw data, calculates aggregated features on this raw data, and serves this feature to other systems, for example, the risk decision engine. So let's talk first about the internal feature system. So this internal feature system was built by many and many extremely clever people throughout the years. I will thank all of them. I can't even name all of them. There's been so many people. And we built it. We know how it works. We know it can do the job. It is a well-traveled path in a sense. It is Java-based, which is, in a sense, an advantage on the back end, because it was built to be very fast when it was originally built. And we have, however, being Java-based, it is a bit less machine learning and data science friendly than something built in Python or PySpark, because typically machine learning and data sciences have more experience with Python and PySpark, and they're more familiar with it than Java, which is, at least in my perspective, it's a more common programming language for people coming from the software engineering sector. So one more advantage of the internal feature store is that it would give us soft guarantees on the latency of the entire feedback loop. And here I'm saying soft guarantees in the sense that we built this internal feature system, we have used it so many times, we know it can provide very low latency, and it typically does provide very low latency successfully. One of the disadvantages of the internal feature system is that ingesting this new data feed of risk evaluation, it's a very, very high volume data feed. And so there were concerns about it. Every time that you have a system and you're about to test it to, make it ingest something that is a higher volume than before, or, a higher speed than before, there's always some concern, even if it could turn out well. So this is a perspective on our internal feature system. On the other hand, we have Tecton. So the main concern with Tecton when we started this project is that it was a very unexplored feature store at Block. As a matter of fact, the first stream feature view that we built as part of this project, I believe it was the first real production stream feature view at Square, if not at all of Block. So because Tecton was still a very unexplored road at Block, we didn't really know whether there could have been blockers down the road, whether Tecton can really provide the low latency we're looking for. In a sense, there were unknown unknowns. We hadn't used Tecton that much at that point. On the plus side, there were a few things we really liked about Tecton. One of that is that it is part-based. So it guarantees excellent parallelism with no bottlenecks. The storage is cloud-based, backed by DynamoDB, which is one of the choices that Tecton offers for storage. So we don't have to worry about auto-scaling. We don't have to worry about storage, space, and so on. It's all handled by Tecton. And another advantage, of course, is the fact that features can be written in PySpark or even SQL. For machine learning and data scientists, these are way more familiar programming languages. And so it's more friendly to the users that really want to write new features. And here I'm taking a very broad perspective. This is not just about risk. This is about essentially every possible machine learning and data science team. Most likely, they have more experience with Python and PySpark and SQL, and they would prefer to use those languages. Finally, another thing that was, of course, very welcome and very helpful about Tecton is that it provides around-the-clock support. And Tecton support is very helpful, and there are people that by now I'm very familiar with. So this was a meaningful pro when we made this choice. And as my previous slide hinted, we went the Tecton route.
So let me just add one more question there. So when compared creating pipelines in Java and the way you were doing it internally versus how you can define features and essentially automate the pipeline creation, how much difference in work for the data engineers did that imply?
That's a good question. I think, so Tecton abstracts some of these parallelism from us, the Spark-based parallelism, the storage through DynamoDB. So it's not just about the amount of work. I think it's more that Tecton makes machine learning and data scientists more self-sufficient. At times, if I had to build the same feature in Tecton or internal feature store, there are situations where if I were to choose the internal feature store, I would not be self-sufficient. I would need another team to get something done for me. So I think that's a big pro of Tecton, that because it abstracts a bunch of things and because you can write your code in Python and PySpark, it makes machine learning and data science teams essentially self-sufficient.
Thank you.
So the second implementation choice we had to make was the data source type. We said we want a stream feature view. That's a given. And we need to choose a data source type. And I think essentially there are two choices here. One is a stream source, and one is a data source function. So let me talk about the data source function first. The data source function is the easiest option. The way this is implemented, and we did test this, is that we have the risk evaluation Kafka feed syncing into the delta live table in continuous mode. So this delta live table is constantly updated with new records in an append way. This delta live table is backed by an S3 bucket, and then Tecton reads directly from the delta live table. So when you define your data source of the data source function type, the only specification you need in the definition is the location of the S3 bucket. So it's extremely easy to define. And another advantage is that the delta live table can be accessed for debugging purposes. I think typically, or at least for us, the delta live table are backed by an S3 bucket. They're accessible through Databricks in the lakehouse. So you can spin up a Databricks notebook, access your delta live table, and make sure that your data is what you think it is. And of course, the downside is that it has a slightly higher latency than the stream source, which I'm going to define next. And then I'm going to talk about why this slightly higher latency. So the stream source option means that you need to actually define a stream source and a batch source. The stream source is the Kafka feed itself. So Tecton listens directly to the Kafka feed, while the batch source is the table where the feed syncs into outside of Tecton. So this is a bit more complicated to define. First of all, if you define the stream, so if you tell Tecton, please listen to this Kafka feed, and for stream source, and then for batch source, please use this table, the two need to have exactly the same schema. And we run into a bunch of schema errors that blocked us for quite a while. And I'm going to talk more about these when I discuss the challenges of this project. So you need to define, effectively, you're defining two separate sources. You need their schema to match. And from the stream source, one of the problems that we had with the stream source and the schema errors was that we couldn't really see what the error was, what was causing the schema error. Again, I'm going to talk more about these when I talk about the challenges. The batch source can be the same delta live table, but at least from my understanding, the Tecton wants a Hive table as a batch source. So the delta live table needs to be registered within the Hive metastore, which is not a big deal, but it's like one additional small hoop that you need to jump through. The main advantage of the stream source option is the overall lower latency compared to the data source function. And once I explain this too, it's kind of natural that the stream source has a lower latency because Tecton is listening directly to the feed instead of waiting for the feed to be written to the delta live table and then reading from the delta live table. So the stream source has an overall lower latency, and that's so important for us that we went through the stream source way. We experimented with the data source function approach. We saw that it worked, but there was an opportunity to get lower latency, and so we wanted to pursue this opportunity.
Can you describe, the change in latency? How much was it?
It was not drastic, but still significant. I think so. I'm going to talk more about the latency and freshness, which I think is essentially the Tecton the same Tecton concept in a few slides. But just to give a preview, ultimately, the most important thing affecting your latency is the volume of your data feed. Much larger data feed volumes are slower than lower volume data feeds. The choice of a source is impactful, but the volume of your data feed essentially trumps most of these smaller improvements. So the other implementation choice that we had to make about the feature view was regarding some specific parameters. And I'm going to talk about some of the parameters that we had to choose between the non-obvious choices. So the first parameter I want to discuss is the stream processing mode. So this parameter of a feature view controls how often Spark takes into account new events coming in when we're updating feature values. And there are two choices: continuous. And in this case, Spark is continuously processing new events as they come in. Every time that you have a new event coming in, Spark is reading this, it's figuring out how that could impact signal values, and it is writing a necessary update to the Tecton online store. So the advantage is that your feature is as fresh as it can possibly be, as low latency as it can possibly be, at least as far as this choice is concerned. The disadvantage, of course, is that it's more expensive because, well, both Tecton cost and DynamoDB write cost are billing you by how many things you write. And so if you write more because you're constantly writing every new update, that's going to increase your cost. And one thing that was a tiny bit concerning for us is that we didn't really find a good way of estimating this cost increase. We know it's more costly, but we don't know really how much. Is it going to be negligible? Is it going to be 3 times as much? We couldn't really tell. The other option is called the time interval. In this case, Spark is processing new events coming in, essentially in micro batches. So if you specify time intervals, there's going to be an additional parameter that you need to specify called aggregation interval, which essentially is the time interval that Spark waits until it ingests the next micro batch. And on one end, this is lowering the number of writes that Spark needs to make to the Tecton online store, because it's only going to write one entry for each user that is present in each micro batch. So if I have, for example, a user which has 200 events in a 1 minute interval, the time interval situation would only make one write for this user, but the continuous option would make possibly up to 200 writes. On the other end, of course, because Spark is only writing an update to the Tecton online store in this micro batch approach, at a time interval based on the aggregation interval, this means that your freshness, like how fresh your data is lower bounded by this aggregation interval. So you can set up this aggregation interval to be as low as 1 minute, but effectively you're giving up a little bit of freshness. And here we made the business call, and we actually went with the time interval parameter with an aggregation interval of 1 minute. Again, this is a business call. We are giving up a little bit of freshness to reduce cost. From a business perspective, we were okay with it because there typically is some time between one risk evaluation and the next one on the same user, especially thinking back at our original example of cash deposit. The user needs to sign up. And once they sign up, they will need to figure out where is the closest location where they can do cash deposit and go there and have the cash attend and so on. So we were fine with an aggregation interval of 1 minute, which lower bounded our freshness at 1 minute. Okay, so the other...
I'm sorry, I'm curious. So you're aggregating at the minute level, and the new transaction comes in. It's obviously not included in that, well, potentially not included in that minute, right? When you're doing the evaluation. So that extra data point comes in as a real-time feature?
Okay, so I think what you're asking is whether the new evaluation that comes in is somehow ingested as part of the request, maybe in the framework of an on-demand feature view. Mm-hmm. The answer is, this is something we're actually looking into right now. But when we started this project, our main goal was to cover all these new product and features that were being launched. So in a sense, the risk evaluation type that we're signalizing, that we're turning into a feature, and the risk evaluations that we want to cover are always of different types, right? We're using these high volume events or bottleneck events, going back to my previous slide, in order to get a prior on all these new features that are day 1, day 2, and so on. And so these are very different things that the user can do. And so we're never really in a situation where these two type of events are so close that this 1 minute aggregation interval impacts us.
Gotcha.
Does that answer your question?
Yep.
So let's talk about challenges and learnings now. And so the first challenge we encountered when we tried to ingest the data with a stream source, this is what I hinted at earlier. We had all these failures of the stream materialization job that was tasked with ingesting the Kafka feed. So these were schema mismatch errors. And the odd part was that the batch materialization job that was processing the data from the Hive table where the Kafka feed was syncing into, the batch materialization job was working just fine. So you could query Tecton for offline features because these are backed by batch materialization jobs. You could even see data quality metrics in the Tecton UI because, again, these are based on the batch materialization jobs, but the stream materialization job would just fail immediately. And this requires some very thorough deep dive by our internal machine learning infrastructure teams, which, again, I'm very grateful to. And they ultimately changed the format of the event published by the Kafka feed from Avro to protobuf. And this solved the issue. One reason that really made the investigation so complex is that it was really hard to determine which field in the schema exactly was leading to these errors. The Databricks logs, in our situation, Tecton materialization jobs are run on Databricks clusters. Databricks logs are not that granular, so we couldn't really see samples of the events as they were being processed and what field exactly was making the stream materialization job fail. It took some time to figure out. It was very complex, and frankly, what I just shared is as much as I know about the resolution of these errors. It was very, very complicated. The second challenge were out-of-memory errors. So this is one of the many places where Tecton support really shined and helped us understanding which parameters we need to tweak to improve and reduce, actually at some point even get rid completely of out-of-memory errors. So in order to share some of the insights, larger clusters seem to help, so more machines, but more powerful machines didn't really matter that much. What really mattered, though, was enforcing a specific Spark partition number on the feature view. And this is something you can do through the stream config parameter of the feature view. So you can tell Spark how many partitions you want it to divide your data through. The real step function improvement, however, happened when we decided to split up our feature view. So initially, we were using a single feature view to calculate aggregates for sign-up model scores, if you want, to calculate or payment model scores, to calculate aggregates for scores of a few different models on a few different time windows. So, you have a few different models, a few different time windows. You need to multiply them to figure out how many columns ultimately your feature view is outputting. And that turned out to be too much to process for a single feature view. It was really clogging the entire process. So we split the feature view into two. Now we have one feature view that is aggregating short time windows and is using an aggregation interval of 1 minute. And then we have another feature view that is aggregating longer time windows. And if I'm aggregating in a longer time window here, freshness is less of a concern. So the aggregation interval can be higher, like 1 hour or 1 day. And this also helps us decrease write costs. And let me touch on this a little bit more. Aggregating over a longer time window, it means, for example, that I'm calculating the average model score in 4 weeks on this user. And if I'm looking at the 4 weeks window, it doesn't really matter if I'm missing the last 1 hour or 2 hours. It's not going to be that impactful when I'm calculating an average of so many data points in such a large time window, which is why we can bump up the aggregation interval and save some write cost at the same time as we decrease out-of-memory errors. So this was a pretty cool learning. A couple more challenges. Freshness was still higher than expected. We moved from data source function to stream source. We made the feature view linear by splitting it up, like I just discussed. At some point, we realized that the bottleneck really is the volume of the data feed. We now have the process that I described in this talk running on a number of different risk evaluation feeds powered by a number of different endpoints. And we see that higher volume endpoints where we have just more risk evaluations ultimately are slower in freshness, so have a higher freshness than lower volume data feeds. And at some point, you can increase the cluster size, you can increase the worker power. It's not really going to lead to yield to meaningful improvements. So this is something where potentially more investigation could lead to an even lower freshness, but we reached a point where, from a business perspective, it was working. It's working just fine. We don't really need to spend any more time optimizing freshness. And finally, the last challenge are transient stream materialization job failures. So there are a number of reasons why your stream materialization job failures job can fail. Some of these are outside our controls. These are, connection errors, timeout errors, permissions that expire, outages on the Databricks side, outages on the Confluent Kafka side that powers our feed, and so on. So these are, outside of our control. We can't really do much to avoid them. And then there are those reasons where we can make improvements to avoid them. One of the main improvements that we made is using an on-demand cluster to ensure that our stream materialization job is not delayed by the cap on the number of machines that are overall assigned to the block Tecton project. This was a new finding when we find out, but there's typically a cap on the number of machines assigned to the project, and if there's no machine available, your stream materialization job will be delayed until there's one available, unless you use this on-demand option. The other learning, which is work in progress, a collaboration between the block and the Tecton team, is to improve the retry logic. When you have a failure, Tecton, of course, has a retry logic, which says, Tecton, please retry the stream materialization job. And we're trying to make this retry logic a little bit more nimble, a little bit more smart. Ultimately, the most important learning around job failures is to monitor every step of the pipeline. You want to monitor the upstream feed before it's ingested into Tecton, so this risk evaluation feed. You want to monitor the Tecton stream materialization job. For example, Tecton provides you the freshness monitoring feature view parameter to monitor it. You want to monitor the resulting feature view serving latency. And you can do this in the Tecton monitoring UI, or you can do this in your own internal system that make a get features request to this feature view. So monitoring every single step of the pipeline. Finally, once we got to the end, we realized that through all this work that was ingesting our own model score, we sort of got a bonus thing that we can leverage. And I think this is related to a question that Sergio had before. So we realized that ingesting model scores can be leveraged by another approach that let's call Bayesian again, for just the theme of this talk. But this time we are essentially comparing risk evaluations on the same flow. So not like before, where we took a sign-up model score and we leveraged it when a user was doing cash deposit. This time we're looking at the same flow, at the same endpoint. So let's think about a theoretical situation. We have two users, two Square sellers who are taking payments. Payments are the highest volume Square endpoint, so plenty of evaluation there. User one fraud scores are consistently low in this theoretical situation. User one fraud score on payments, the median is 0.1, the maximum fraud score we've ever seen is 0.2, and now suddenly user one gets a fraud score of 0.4. Another theoretical user is user two. The fraud score are consistently in the mid to high cohort. The median is 0.5, the maximum is 0.8. User two may or may not have already been flagged for additional review. And suddenly user two gets a fraud score of 0.6. So like every company, we have limited resources at some point. So which one of the two situations is more worrisome? Which one should we focus on? If you're taking a purely non-Bayesian approach that simply looks at the latest score, you would consider user two as higher risk because 0.6 is greater than 0.4. And as I was mentioning before, higher scores correspond to higher likelihood of fraud. But if you look at a Bayesian perspective, the latest score by user one is way more of an outlier than the latest score by user two. Right? The latest score 0.4 by user one is twice as big as the maximum score we've ever seen. while a score of 0.6 for user 2 is pretty much in line with everything we've seen about user 2. So in fact, we probably prefer to invest our resources on reviewing these much higher than expected user 1 score. You can also think about this situation in terms of, from a more statistical standpoint, if you think about mean and standard deviation and so on. User 1 latest score is much more of an outlier. So at this point, we proceeded to implement this kind of aggregations that allow us to compare the latest fraud score with recent aggregates on the same user. And one particularly nice thing about the latest Tecton version is that they have optimized off-the-shelf aggregations, implementing an approximate percentile. So we can surface the median, which is a 50th percentile. We can surface the 90th percentile. We can surface the 99th percentile of all the fraud score for the user for the same model on a time interval. And then we can compare with the latest score, and we can see how it fares compared to the recent distribution of the scores. And that informs our essentially user level Bayesian perspective on whether this user suddenly became much riskier than expected. Okay, so this was my last slide. Thank you, everybody. Thank you, everybody, for inviting me for attending. Any more questions?
We have a few more. Let me shoot a few more questions at you. Can you aggregate shopper features across merchants, i.e. use the ecosystem data?
Did you say sharper features?
Shopper. So the card holder, right? So or the user of the payment app. Can you aggregate their activity across different merchants across your ecosystem?
Yes, we can do that. You can do it through Tecton. You can do it through your internal feature system. This is a pretty common thing to do in the financial ecosystem.
Okay. Another one, is there a single decision engine, or is there an engine for every product feature?
This is a good question. Ultimately, it doesn't really matter if there's a single decision engine or multiple ones. What matters, and is something I mentioned earlier, is that every product or feature has their own separate endpoint. And when we get a request through this endpoint, a different set of rules and models are evaluated. Whether all these endpoints are hosted in the same risk decision engine or a number of different ones is not, I don't think it's that important. But it is absolutely all different models.
Okay. Also, are the risk evaluation requests that come in, are those blocking requests, or is it a synchronous request, or is it an asynchronous request?
That's a great question. We have both types, synchronous and asynchronous. It really depends on the use case, on the experience we want to provide to the user.
Perfect. These are emails about a video. Okay, is the Bayesian approach as effective in mitigating the fraud risk for new customers who have fewer events for risk evaluation model, or to update compared to returning customers who have a longer history?
This is a great question. It is effective for both, but it needs to be used in somewhat different ways, right? So what we discussed today is essentially the implementation of a very general approach. But now, the nuances, you'll need to iron out the nuances based on what exactly you're targeting.
So there's a follow-up to the aggregating shopper features across merchants, is how do merchants feel about that?
So merchants expect Square to protect them from bad actors and fraudulent users. And fraud is one of the reasons why fintech companies like Square and others have the legal right, up to a point, to leverage user information to protect the users themselves, to protect Square, and to protect the ecosystem as a whole.
Okay, and I think we have time for one more. Says Square, Cash App's ML Infra. Can you talk more about what are the most difficult challenges it aims to address, and a little bit about your roadmap?
That's an excellent question, but unfortunately, I'm not the right person to answer, because while I collaborate very closely with the block machine learning infrastructure teams, I am part of the fraud detection team, so I'm essentially a customer of those teams. So I can't really speak for their roadmap.
Understood. Well, thank you again, Niccolò, for this presentation. I thought it was really interesting, and thank you all for attending. We're at time now, so that was the last question. Thank you.
Thanks, everybody. Bye.